Okay, so previously we talked about the difference between a packed column and a capillary column, and we gave you some dimensions and we started discussing the differences between the two and which one's used more and more often. Up here at the top, this is a picture of a capillary column. Very thin, traditionally brown in color, and it gets coiled around on this metal cage that gets installed into the GC system itself. Here in this next slide, these are pictures of packed columns, and you can clearly see the difference between them. These are metal traditionally and material wise, and these really aren't put onto a cage, and they're very rugged and they're very rough as far as you can't really bend them a lot. And these get installed into the GC system, and they do the same job that capillary does, but this is more old school. I need things that will do better separation. I need things that can handle very complicated samples a little bit better. And a packed column just traditionally doesn't do it for me, but capillary does. Down here at the bottom, these are just additional pictures of different packed columns. So I see packed columns here to the left and a packed column here to the right as well. So traditionally, stainless steel, they're much shorter and they're much wider. And then when I look at capillary columns are much thinner and they're much longer. And they traditionally go onto these cages because there's so much of it, and they are brown in color for the most part. We talked about the filling of the packed column, and we said diatomaceous earth is also used. So here's microscope images of, or magnified images of diatomaceous earth, and I told you that these things were very high surface area. I told you that they were porous like a sponge, and my sample will go through them little bit by little bit as it travels through the column. Here's a closer look of these little critters. And these are packed inside of the column. To you, it looks like white powder, but if you look at it closely, it's nothing like white powder. So again, they're sponges. And the molecules of your sample go into these little holes and go into these little crevices, and they travel through the column slowly and come out the other end. So that is the filling inside of a packed column. Diatomaceous earth, or something that we would call chrome absorb. Now, not all chrome absorb is diatomaceous earth, but it is one of the common materials that can be used for packed columns. So now we need to talk about the stationary phases and the different versions for capillary columns. Okay, so capillary columns are much thinner. They're the ones that are used the most common. I keep saying that over and over, but these things have different versions of stationary phases on the inside. So there's three forms of capillary columns. One is called W-cot, and one is called S-cot, and one is called plot. Scott, plot, W-cot. I could almost make a rhyme out of that. All right, so we need to talk about these three different variations. And with these variations, they're slightly different, not much. So this is traditionally always a problem for people. The W version stands for wall, and the C stands for coated. So it's probably something that coats the wall, right? Okay, use some common sense. The S cot is support. That's what the S stands for. Coated. So it's probably like a wall coated, but it needs a little bit of help. And then the plot, the P stands for porous, and the L stands for layer. All right, so these three things are slightly different. Now, what does the OT stand for? Well, it stands for the same thing in each case, and it's called open-tubular, man. All right, so why is it called open-tubular? Well, tubular probably means tube. All right, so here is the capillary column. I went kind of crooked, but that's okay. I'm having one of those days. Open tubular means that the majority of the column is empty on the middle, and wall coated basically means that I've got my stationary phase that is smeared along the internal walls of the column itself, and it's open in the middle. So that is a wall coated open tubular column or stationary phase makeup. These things are coated very thinly on the inside. Okay, it's a smearing of stationary phase. Now, support coated basically means that I have taken this setup here, and maybe that's not really good enough. And this setup is basically glue that I can then put maybe some molecules on to help me with the separation process. So this is a modified form of a stationary phase. And I use my existing thin film and I put some compounds on it that will help me make a better separation. And this is what we call the Scott, support coated. I've modified it in such a way that it makes my life a little bit easier. And then finally, we get the plot. And the plot is porous layer. Okay? So with the porous layer, you traditionally see stationary phase smeared across the internal walls of the column itself. And then you can come through and make a sponge with it. So you traditionally take this and you create a very porous surface along this coating of the capillary column. And we call this porous layer because of that. So see, I told you that these things were not very complicated. The names kind of tell you what they do, and this allows the molecules to kind of come through and go through some of these openings throughout this jelly-like material as it makes its way throughout the column. So, in the slide, you will see maybe a better picture or a better drawing of each one of those. Let me see if I can find it. Here it is. And here is my wall coated. And then here is my support coated. And then here is my porous layer. All right. So those are the three different versions of capillary columns that you might see. And wall coated will be the most common. Let me change my color. Oh, wall coated is the most common. Okay? All right. So capillary columns are coiled around a cage. They're all made that way. The flow rate with these capillary columns, very large for a packed column, but here we're looking at 5 to 15 mils a minute. And this is the total flow rate, not the column flow rate. So it doesn't take a lot of gas to pump through these columns. And again, it's because they're so narrow. And because of that, they can't hold a lot of gas that comes through. For a GC, it's very common to have a 530 column. This 530 is the internal diameter of the column. We call them 530s. So 530s can be used with many different detectors, many different injectors. They're a little bit wider. They can take a little bit more flow as far as your helium goes. And because they're wider, they can take a little bit more sample as well. But you can go smaller. Remember, we said that we can go all the way down to 100 micrometers instead of 530. So we can get them narrower and narrower depending on what we need and what we need to run. Okay, here is a summary of the different GC stationary phases and the types of columns. So here we see packed columns, and the packed column is the stainless steel column that was originally used back in the day. And if we go over and look, you traditionally want to inject about 10 microliters. Nothing really any lower. 10 micrometers is a really good start, at least in the beginning, to figure out if it's too much or if it's too little. But these have very large sample sizes compared to some of the others. The open tubular, these are my capillary columns, right? And the open tubular columns can come in different forms. We said 530, which is 0.53 millimeter, or 530 micrometer. It's the same thing, just different units. The 530 columns, which are the most common, we call those wide bore. And those can hold about 5 microliters. So you can inject a little bit more, but about half of what you can on a packed column. I can get a 30 or 320 size. The 320 we call medium bore. That's typically a 2 microliter size of sample that can be injected. Then we can have a 250 column that's called a narrow bore. And those really take 1 microliter of sample. And then we can have a 100 capillary column. And those are ultra narrow bores. And those can take about 0.5 microliters. So this gives you an idea of the sample injection amount depending on what types of columns that you're using on your machine. The stationary phases, well, what are they, right? Well, these things are typically two big stationary phase classifications. Polysiloxanes or polyethylene glycols, and we can call those PEGs, P-E-G, polyethylene glycol. And down here at the very bottom, that's the structure of a traditional PEG or polyethylene glycol for you. And then up here at the very top, these are just different versions of polysiloxane. So dimethyl polysiloxane, diphenyl dimethyl polysiloxane, cyanopropyl dimethyl polysiloxane, or trifluoropropyl dimethyl polysiloxane. There's hundreds of these that actually exist. So polysiloxanes is just an umbrella. And underneath that umbrella are different variations of stationary phases that can be on the instrument. And it just really depends on what you need. What are you trying to separate? Because there's a column out there for you to do what you need to do. Okay? So this is where I'm going to stop. And we'll pick up with polysiloxanes and polyethylene glycols in the next video. And we'll continue to talk about the differences of the column on the inside of the machine.